各位老师、学生、贵宾，大家好。好，我想我今天基本上我会用英文讲，就是前面就是讲几句中文啊。第一，我要你们有些人知道，可是有学生可能不知道，我的指导的受主是刘老师啊，所以今天有一点压力，可是。但是平常的压力有点奇怪，可是今天刘老师的指导教授就是吴斐丽老师，所以今天的压力特别大。你看我有点紧张，那你要知道为什么这个。可是后来我在想，其实压力不是在我，压力最大的是在吴老师那边。所以我讲的不好，你要去怪他，他会怪吴老师。Okay, so thank you, Professor Liu, for organizing this, and the others who organized it. I'm very happy to be here and be able to say a few words. I'm going to talk about the center we have called CURRENT, which stands for Center for Ultra-Wide Area Resilient Electric Energy Networks. And really, it's a center about wide area control. The ultra-wide is, I guess we needed something new, because wide area control has been around for a while, so we wanted to, now we're being serious, I guess. But really the idea is about how to do wide area monitoring and control. So let me say just quickly what the center is. This is an engineering research center funded by National Science Foundation, Department of Energy in the US. And it's ostensibly funded for 5 years. Hopefully we'll have it for 10 years, which means that we should be able to get some impact over the life of the center. It's a joint industry and effort along with that, so we have industry members. And then it's several universities. So some of the things I'll talk today about are things that are being done in the school. So our partner universities are Rensselaer Polytechnic, Northeastern University, and Tuskegee University in the US. And then the host is our school, University of Tennessee. I think the one thing I want to come around with is, as a center, we have many opportunities for collaboration. So hopefully, some of you will get a chance to come visit us. Okay, so why the center, this ultra-wide area control? Well, when we started first thinking about forming the center a couple of years ago, it had been obvious that energy sustainability is one of the most fundamental societal problem challenges. There needed to be some ability to reduce the reliance on fossil fuels. And as we looked around, most of the solutions that people were proposing were either on the source or the load side. So on the source side, renewable energy sources, investment in wind or solar power. And on the load side, it could be electric vehicles or storage. Consider that type of load, or it could be on the efficiency side of buildings or lighting. And if you look at that emphasis, what we concluded was that any one of these things are important, or they are all important to achieving the goal of energy sustainability. But what they all require is a fundamentally new approach to electric power transmission, and particularly emphasize transmission. And I'll try to justify that a bit, since many of the discussions are about distribution. So this is a map of the U.S. Showing in the upper left-hand here population density. So we can see very heavily densified in the northeast, on the two coasts, pretty empty in the center of the country. And then these two maps are showing the resources in terms of wind and solar. And so good wind sources with darker colors here for the center of the country, that are solar in the southwest and west. And if you try to overlay these, to these maps, I think what you see pretty easily is that where you have good resources for renewables, for wind and solar, you don't have a lot of people that live there. So that's less true with the solar, but it's definitely true with the wind. So there's really only two solutions. Either you get people to move, an industry to move to where there's that energy, or you move that power to them. Well, if you've ever been to North Dakota, probably not going to be the most attractive place to move to. It's going to be more attractive to move that power to where the people are. So we want to take advantage of those. We have to move that power over a long distance. Another consideration is, this is kind of generic about blackouts, but generally, when you have major outages on the transmission system, they're very expensive. So if we're going to be moving power over longer distances to incorporate these new renewables, most likely we're going to be putting stress on that transmission grid, or at least asking it to operate in different ways. And we don't want to do that at the cost of incurring greater blackouts. Okay, so overall, for the center, then this is our vision, is we want to have this perhaps nationwide or continent-wide system that we can control in order to move these renewables, new renewable sources, move that energy over long distances. But of course, we want to do it with all the good things still intact. We want it still to be reliable, still to be cheap. We want to take full advantage of whatever other resources there are, whether it's storage or load. And then as our center is also emphasizing education, it's also important that we train the next engineers appropriately for that. Okay, so say a few words about what exactly is current, or what's different now that makes this available. As I said in the introduction, wide area ideas, wide area control, it's been around for 30, 40 years, I guess, late 70s, early 80s, people first started talking about wide area ideas. And the first thing is new measurement and monitoring. These are showing locations of PMU measurements in the U.S., either planned, I think these are planned ones, so within the next few years we should have a couple thousand, I think this is the first initial planning of 9,800, but in a relatively short amount of time we should have an extensive amount of PMU. So PMU measurements, for those who are not, I mean, for power students in here, right? By having that phase information, allows me a snapshot to get the state of the system. So that's a very radical change in how we're able to monitor the system. Now, the other thing I listed up here, FDR, is my colleague Liu's developed system. It's a frequency data recorder, and that's a poor man's PMU. Basically, it's a single phase unit that you can plug into the wall, and you can measure frequency and phase external to the grid, but it also provides you information. So that's probably the biggest technology advance in the area of monitoring that people are thinking of. But actually, it's not really just limited to that. You now have ability to monitor, say, line sags in real time, weather variables, lightning. That's fairly common in control centers now to have be able to track lightning as it moves across the system. And so there's a wealth of information that's available now that wasn't there before. Okay, the other big change for the grid has been in communication. If you look at what's in the United States today for the power grid, it's primarily based on 30, 40-year-old technology. There's polling different points around the grid, so the control center getting information from RTUs at a relatively slow rate, 2 to 4 seconds in the U.S. is typical. So there's relatively infrequent updates to the control center, and then fairly limited in terms of what the information comes back. You're not getting time domain waveforms in this active control center. And then it's all hierarchical coming back to the control center. Well, we have the ability, of course, now in modern communications to do much more than that. So that's a radical change, I think, too, for the grid. And then the third thing, I guess, that's fundamental change, or a reason we can start thinking seriously about wide area control, is the ability to actually change what goes on in the power system with new actuation. So for my purposes, actuation is anything that can change power flow in the network. So that could be just your traditional generation controls, whether they're stabilizers or whatever the generation settings are. Or it could be your infrastructure like HEVDC. It could be, or fax devices, so flexible AC transmission systems. Or it could be newer things like storage, which can provide power at the times you want it, and even the renewables themselves. So we typically think of the renewables as being stochastic, and they are, but through the interfaces, through power electronic interface, we have some ability to control those. So these are actually another part of our control system. In the simplest way, we could be still, wind, or disconnect, but also by, say, switching from reactive power injection from real power injection, we can maybe get support voltage as opposed to providing energy to the system. So my animation is a little bit slow here. If you really look at what the center is about, it's about control. So fundamental for control, I've got to have some observations, some monitoring, ability to move that information around, and then once I've got that, if I'm able to figure out what to do in terms of control sense, then I have to actually be able to actuate something, be able to do something. So that's our that's what our center is about. Oh, I'll go back. Eventually, I want to today talk about two applications of this, but do a little bit more sort of background in terms of where we're at in the system now and where I think it's likely to be moving. So if we think of today's system, this is showing the three synchronized grids of the U.S., just emphasizing that in the U.S. anyway, you can't really move power between these. In the future, maybe we can with HVDC links. There's a couple of various plans that are out there. But if I look at what's on the system, they're relatively low amounts of renewables. Even with the rapid growth of wind, it's still a relatively small percentage overall. The transmission network itself tends to be relatively flexible, operates with a fairly large capacity. At certain times it may be up to its capacity, but most of the time it's not fully utilized. Professor Wu talked about this morning, we've got generally generation following load. And then the overall operation tends to be pretty local, meaning that what's maybe happening in Washington is not very clear in California. So most of the information stays fairly local. Okay, consistent with that, if you look at the set of controls, and I'm not going to go through all these, but if you look at what's built up over the history of power systems, primarily a lot of local controls, and there's good reasons for that because that's where you've got the best information. Historically, we weren't able to move that. But if you look at these controls, probably the only non-local and closed-loop control that's out there is automatic generation control, because you do it between the control areas. There are some protection schemes, some special protection schemes that use some wide area measurements, but a few things like pilot relay, maybe it's not a local measurement. But for the most part, they're local. And then there's a few other things that are open loop, say economic dispatch and that, which you gather information from a wider area, but they're not. So there's two things to notice about this. One is if we can take advantage of this information, perhaps we can do a better job of these controls. And maybe we can reorganize these controls a little bit to be perhaps less complex or maybe more reliable. If I think about communications and monitoring, again, I mentioned the communications is relatively slow in the system today, several seconds. There's some point-to-point, but typically information has to flow between the control center, between points in the system, and not point-to-point. In terms of what's monitored, at the higher voltages, it's pretty complete on the voltages and currents. Lower voltages, not so much. And then if we start getting into more specifics at the lower voltages, things at substations, relatively little, well, at least what's available at the control center, there's relatively little monitoring. Okay. So this is, generally speaking about what we have today. So it's fairly inflexible in terms of communications and pretty limited in scope, and then also limited in terms of what's monitored. So if I think of what we might have in the future, then it's going to be sort of all these things I just mentioned sort of changing. This is a map from the Department of Energy, sort of their vision of what the future grid may look like. And the idea of this structure is that it's maybe certain areas which are closely synchronized and with some maybe more heavily loaded paths between them, but then some sort of independence in these areas. So some availability to transfer, but then not such tight coupling between areas. So there's some infrastructure things that may change, may make the system more flexible and perhaps more reliable. We expect the possibility of very high penetration of renewables, again, not traditional renewable like hydro, but variable sources like wind and solar. And then load and source variability, so responsive load, and it's not just a generation tracking load. And then we expect that high situational awareness, meaning different parts of the system will be able to see what's going on. I want to make one other point, I guess I can make it here. You know, when we started our center, there was a big emphasis on the renewable energy sources, but in the last year and a half in the US, the biggest change has been in switch out from coal to natural gas. So we've had a very rapid changeover switching coal units to natural gas. And the price of gas is very, very low in the US. That's the cause of that. So you may think, well, this could also push out renewables, which is probably possible. However, I want to emphasize that I don't think that moves us away from this concern of wide area control. Because, first of all, just the rapid change of this occurred gives you an idea that the key thing that we need for the future grid is that flexibility, about being able to adapt to some changes. And that may mean that your transmission system is operated slightly differently, and its ability to be able to adapt to the conditions that's important. Okay, so other things, and I think about the future grid then. So what are my controls going to look at? Well, it should be some sort of context for that local control, rather than just the local measurements. It should have some understanding of what's going on in the overall system. So whatever you do locally supports the global structure, the global needs of the system, whether that's it's a stress situation and it's providing whatever sources are needed. Then how we break down the different control schemes should be less dependent on the structure we had historically, say, between small signal stability, transient stability, voltage stability, and more dependent on the device, since we have devices which all operated very different, potentially operated very different time scales. So storage may be at one stable scale, a wind unit maybe fluctuations may be at another time scale. And so that means a greater diversity of controls with those. Okay, so similarly for other things, I expect a number of different things, and I don't want to go through all these, but I think the likely future scenario is one where we have still local controls, because that makes sense and we want to close the loop and not worry about delays and other interruptions. It makes sense to have things locally. But still guided by the system, and more things should be closed. We expect more of those controls. When it comes to communications, then we expect the likely scale will be gathering more than just 2 to 4 seconds, and maybe gathering waveforms. So with PMU measurements, maybe you're getting 30 samples a second. So you reconstruct the waveforms, and that may be available in the control center, may be available between 2 points in the system. And then there's really pervasive metering throughout the system. And then the issue is no longer is that information out there, it's just which information is getting where. So rather than not having any monitoring at all, it'll be, we have all the monitoring you want, it's just choosing what it is. Okay. And then the types of monitoring you expect to change. So whether that's temperature, line tag, all sorts of different variables that people so anyway, this future system that idealized perhaps, but something that's fairly flexible and broad scope with okay, so then I'm going to wrap up my introduction here with just an example I'd like to show to students, which is that there's generally an acceptance that building new transmission has value, building new generation has value, but there's a lot to be said for improving the controls in the system. Just talking about where I used to be in the Pacific Northwest, we initially built the transmission lines between the Northwest and California. It was designed for, well, the AC line had 2,000 megawatt capacity and 1,400 on the DC line. But when they actually built those lines, as I understand before my time, the actual capacity was much less. And that was really from misunderstanding of some of the dynamics, primarily through the ADR, the automatic voltage regulator. So that was providing some negative damping torque and resulted in inability to move power to California. So after through addition of stabilizers, later on some things for transient stability, they were able to increase that above the original design. So this is just kind of broad overview here, but the point is that the controls, and improved control has a real value, and that ability to model things correctly, and that can be just as important as building new transmission. Okay, so let me say a little bit more about what for our control center. Then, we're looking at 4 areas here of interest: monitoring, modeling, control, and actuation, and we're doing work in those, and we're trying to address things in each of them. So I'm going to show you a couple of examples today of some work going on. It's primarily going to try to combine a little bit of the work in terms of controls and monitoring the system. One a little bit further developed than others. But I want to do that before I look at those 2 example applications, is to show a bit of idea of work. Okay, so what I'm going to show is this is a generator that's going to trip here in Florida. And I'm showing a map here. It's about a 500 megawatt generator. What I'm showing a map here is this is from Dr. Liu, my school's frequency monitoring system, spaced out here. And what it shows you is how it takes a while for that disturbance to propagate out. So this is just a map of the frequency disturbance. I'll show that again. And I think the important thing is show that an event that happens here has an effect far away. It takes a while to get there, and then even after things have really died out here, we're still having things oscillate out here. So this is relative real time. It takes about 2 seconds to move from Florida up into the Northwest before you get to the full effect of it. So it's 2 seconds. That's time if you anticipate this to do something. And so that's an interesting thing, but so if one's monitoring variables here, frequency and phase, then perhaps we can do something before it gets to the outer reaches of the system. Okay, so show this partly because it motivates what I do, but plus I think it's a cool picture. It's very easy. All right, so I'll do 2 example problems here to show the things we're looking at. One of them is slow, I'll call it a slow control. It's one that we know how to do well already, AGC, so basically frequency control. And this is an easy one, but I'll make up for being easy by putting in lots of theory. Although the theory is really there just to kind of motivate the approach. So what I'd like to sort of throw out as a provocative question is, can we perhaps just get rid of the idea of control areas and at least the area control area, so kind of a counter to what we heard this morning from Professor Wu. Although it's really not in contrast, it's just a matter of does every device that helps us with frequency control in the system necessarily have to be on a typical sort of A switch. And so what I want to do is then look at a local control for the frequency, and then how, using PMU measurements, how that looks relative to the system. and then think about ways we control the system. And the other thing I want to do about this is think about, is it possible or valuable to eliminate this division between traditional economic dispatch and frequency control? If they're both about settings, maybe this is one thing that I can just do, combine. In fact, could I not only combine economic dispatch frequency control, but also overall security? Okay. So this is work being done by my student, Mariam Veriani, and it uses some fairly sophisticated control theory, which I talked about a little bit, but it's really the idea that just gives us a motivation for doing control. Okay. So back to renewables a bit. What are the main challenges? One, they're less predictable. They may be far from the load center. We have to move power, far distance. They generally don't match our load variation very well. So when we've got a lot of wind at night, we don't have much load and so on. Because they tend to actually be non-responsive to frequency or be negative response, so give us the wrong input to that. And while it's less likely for a unit to suddenly fail, there's more, the disturbances of the system tend to be more correlated. So it's tend to be, if I get a sudden drop of wind, it's going to affect many plants. So it has to be handled a little bit differently than a traditional generator. Okay. So control structure, what we're talking about is this idea of sort of contextual and local control. So the context is something at the high level of the system, so still have a control center. Choosing some overall reaching goals that reflects the basic needs of the system. Maybe that's economics, maybe it's everything's operating normally. If it's a stress system, maybe that's more security-based, there's some constraints. And then offloads the particular controls to the local decision, where more detailed information and understanding of what's being controlled. And so it's a little bit different than in hierarchical control, in the sense that I'm not really telling this local controller what to do, and I'm also assuming the local controls can gather information as they need. Okay. So this is the control structure. Some overall contextual control. There can be many levels of these, and then based on what that context is, I provide that information to the local controller, and it appropriately does it. And now the theory part of this is what we wanted, really where we came at this was from a nonlinear control theory, which is what does it really mean for something to be easy to control? There's this concept of flatness, which is essentially extensive controllability for nonlinear systems. It's really two ideas. One is you want to choose your outputs of the system so that the system you're controlling is easy to control, and then also provide some ideas about trajectory planning. So in this sort of framework, the flatness is a theory we'll use to say, okay, what is it we want to observe on the system, and then what we're observing, what sort of path do we want that to take? Okay. So this is I guess I said some of this, but basically the key insight of this method is trajectory planning, and then it turns out for our problem there's also a decoupling between the local controls. Okay. So I'll do a little bit of theory here, but like I said, really, we're not so much using this theory here to do a whole lot, except to give us the inspiration for how we want to organize the system. So the essential idea of flat differential systems is that if you choose your outputs such that you can find the state of the system from that output and its derivatives. So flat over here is y, and if I look at the derivatives in that, and then the inputs and derivatives, if I can reconstruct the state from that, so I get derivatives from that, then I don't have a need for a dynamic state estimator. Okay, so control people tell me that's important, and I think that's true. It's sort of like if I can find what I need to know about the system entirely algebraically, then that's a good thing. And I'm going to be able to track what's going on better. Okay. And then the trajectory generation part, there's this is just generic here. I'm going to move from some point now to some future point in time. And I'm going to I've got this objective for each of my local controllers, and they can decide how they move from point to point, and using some sort of a control algorithm. Okay. So I'm going to apply this, like I said, to AGC. So fairly simple control problem we can solve through another way. This is perhaps a different way of looking at it, but I do think it gives us some benefit in that it's got a very simple structure, and it tends to do better with uncertainties in the system. So in this control, in this example, using the flat concept, the local control is going to be whatever that, if it's a traditional generator unit, it would be the turbine, the governor controls to maintain frequency and tracking. And then what I'm going to get from the control center, rather than using the air control air, is I'll get something about where that I want that unit to be in the system, and then I'll let the local unit to decide its own particular performance. Okay, so the map I have here, this is basically just going to show that the simple fourth order model of a generator, the governor, mechanical power input that I might use for understanding the AGC loop. It has to be re-frameworked in terms of flat outputs, and essentially what this says is that in this case, what really is the flat output is the rotor angle. Okay, so if I can measure, I can't measure directly, but I can estimate the rotor angle. That gives me enough information that with that and its derivatives, that I can say what I can do whatever I want to with the control of the system, or at least algebraically I know what's going on in the system, and then I can control it. Okay. Now the control design, well, and it turns out that this is the decoupling of the system. So I decouple the generator units by having. So then the control design could be independent of that. I basically just use that theory to say what it is I want to look at. So I want to look at the phase at the terminals to get the rotor angle, and then I want to provide a trajectory for that. So each of those trajectories is going to be calculated separately from the generators, but that trajectory is going to be, the trajectory I'm providing there is that it's relative phase in the system. Okay, so obviously this is leading to the use of PMU measurements. Okay, so I've got whatever the perturbations are in the system, load changes, generation loss, wind generation, solar variation, all those things. And then I'll have locally each linear controller, well, whatever method it uses, I'm going to use a simple yard method to design a controller, but it's going to track that. Okay, so that control structure is basically a local measurement of the phase, then with some global information about the plane. And I compare that to a traditional sort of AGC type of, based on area control error method, where I've got the frequency coming in, that's a control center, I've got something about the frequency response characteristic system, I'm looking at the timeline schedules, then I use some sort of interval control, and then based on the various participation factors and units I extend them out. So it's not horribly complex, but it requires some involved coordination between these, and I think more complex than what we want for, say, a simple controller like a radio somewhere or a small generator. Okay, so here's the overall structure. I still have some control areas here, some generator allocation by area. There, I break down into each of the different generators with their the information they need to create their own planning path, and then their control is done. Okay, so let's look at an example, see what that looks like. It's a simplified version of or simple version of the New England system in the U.S., broken into 3 areas, 39 buses. And I'm going to add some wind generation in there with some variability based on some actual, not from New England wind, but from we got from another system, so reasonable variability to that system. And I'll look at essentially 2 cases here, either relatively to no wind case, then 10%, 20% in there. And then I back off on the generation in those areas as I add in. So, these are typical when you do simulations. It looks obviously both is good, but the important point here is that with this sort of localized to contextual control, I tend to chase the variations from these disturbances less. Okay, and so without information about the pipeline flows, all I'm using is this trajectory information based on where I want to be relative to the system phase, and the other one for the traditional air controller on that. Okay, and things tend to stay local. So the variations in frequency when I have load change or wind fluctuation change in one area, the damping or the control that tends to stay local. That comes out of it. So this is one example. Obviously, I choose something that shows good performance, but this tends to be reasonably true. It tends to work out in most of our cases. And this looks like, even though we're not monitoring the tie line flows, that actually also tends to track pretty well. And then as we go up into even higher wind penetrations, now you're seeing the traditional controller also tending to chase the frequency more than really necessary, and then the proposed controller providing reasonable response. And again, the tie line flows are showing good performance relative. Okay, and then also there's things we can do with the timing. So I've got one more example I want to get to. So the whole idea here is that this is a fairly simple control problem. AGC has been solved, but as we get to more variability with alternative energy units and they've got some challenges. Frequency response is getting worse in the system, and this is a very simple control that seems to be one way, effective way of kind of coordinating that frequency control without forcing the traditional air control. Okay, so now I'm going to do one more example in the 5 minutes or so that I have left, which is a little bit more advanced, but or much, I should say, much harder control problem. So I'll handle that by being, we're not as far along in it, but it's kind of an interesting problem, so we'll look at it. So I think about the faster phenomena, a little bit like the video I showed earlier, is can I stop that propagation of that disturbance? And sort of motivation thing, or motivation area